finished yet. It takes a while to grade that many. You can expect them to hopefully be done by Tuesday. Now, hopefully everybody remembers what we did in last thing. What did we go over? Nobody remembers? Did you say Calvin cycle? Next, well, last Thursday was review day. Last Tuesday. Did we start with the Calvin cycle? I think we did. But what was the last chapter? Mitosis. Very good. What is mitosis? Yes. So simple way to define that would be cell division or cellular reproduction. Now it turns out there's another type of cellular reproduction. So when you use mitosis in order to divide, you're producing two cells that are both going to be genetically identical to each other and to the same cell you started. But in order for sexual reproduction to be possible, another type of cell division had to evolve, and that's what we're going through today. So first, a little bit about sexual reproduction. It evolved shortly after the appearance of eukaryotic cells. You don't see this in prokaryotes. This should come as no surprise that sexual reproduction is extremely widespread. It is nearly ubiquitous among eukaryotes, meaning almost all eukaryotic organisms are capable of sexual reproduction. It is ubiquitous among animals, meaning that every animal we know of is capable of sexual reproduction. And it's almost exclusive among animals. There are a few that are capable of asexual reproduction, but not very many. Can anybody name one? Nobody? An animal that can reproduce asexually. I'm not sure if cockroaches can do it. Sea stars can. You know, if you cut an arm off of a sea star, that sea star will grow a new arm, and that separate arm will grow a whole new sea star as well. So that's reproduction through something called fragmentation. There are a few other types of asexual reproduction seen in animals. I think we'll get into that later in the semester. Anyway, why is sexual reproduction so common? It's kind of inconvenient. There are a lot of disadvantages to only being able to reproduce sexually. What's one of them? Big problem a lot of people have.
You're going to have to use up energy to find a suitable mate.
Yeah, you need a mate. You may have to expend energy to find one, or you may not be able to find one, especially if you're some kind of animal that lives in a really sparsely populated region. Another one is that in most cases, only half of your population is even able to give birth. That's what limits the birth rate in populations of primates, for instance. How many females are there? So, given these disadvantages, you should think that sexual reproduction would be a lot less common than asexual reproduction. You would think that reproduction rates are much lower in exclusively sexually reproducing organisms, and they generally are. So why did sexual reproduction evolve in the first place? Why do we use it? What advantage do we get from sexual reproduction? Yes?
Well, the idea is that you'll get variation in the hopes that your offspring will be more better adapted to.
There you go. Increased genetic variation. If you reproduce asexually, all of your offspring are going to be exact genetic clones of yourself. There will be no genetic variation whatsoever. However, if you reproduce sexually, your offspring will be some genetic combination of you and your mate. That creates new genetic combinations that never existed before in your population, and gives you the possibility, not necessarily a probability, but a possibility that your offspring may possess a more beneficial combination of genes than you do. So I promised to teach you guys about the other type of cell division, and we call that meiosis. This is necessary because obviously sexual reproduction requires fertilization. Fertilization meaning two cells have to fuse in order to become one cell. We generally call those two cells what? Somebody else decide. I feel like I'm talking to one person. Yes, what do you got?
Zygote?
No.
No.
The cell they make is called a zygote. What two cells fuse to create a zygote? What do you got? Gametes, or sex cells. Or if you want to name specific types, eggs and sperm. We generally call the female reproductive cell an egg, and the male reproductive cell a sperm. Now it's completely, massively important in sexual reproduction that those gametes, or those sex cells, or those eggs and sperm have half the normal number of chromosomes. Who remembers why? I think I mentioned this last week. Somebody from the back. Hopefully you guys did the reading as well. I almost had a pop quiz today. Just didn't want to do that to you the day after exam. But there might be one Tuesday. You should come to class every day having done the reading. That's the whole point of this quiz. So the reason it's important is because if you had gametes that had the normal number of chromosomes, which in humans, for instance, would be diploid, 2 copies of each chromosome, then at the moment of fertilization, when you create a zygote, how many copies of each chromosome will that zygote have? Now this is basic math, I expect you guys to know this. Not 2, 4. If each gamete has 2 copies of each chromosome, then the zygote will have 4 copies of each chromosome. And then when that zygote develops and is born and grows up and has children of its children will have 8 copies. And then 16 and 32, and pretty soon you've got more chromosomes than a cell can hold. So in order for sexual reproduction to exist in the first place, we have to have some sort of method for creating gametes that have half the normal number of chromosomes. And we call that meiosis. Now the mechanics of meiosis, the nuts and bolts of it, are very similar to mitosis in a lot of ways, because it is still cell division. But the big difference here is that instead of resulting in 2 diploid daughter cells, it results in 4 haploid daughter cells. Haploid meaning 1 copy of each chromosome. So the chromosomes get duplicated before division, just like they do, or at least very similar to the way that they do in mitosis. But after that 1 round of chromosome duplication, there are 2 rounds of cell division without a 2nd chromosome duplication. That's how you end up with half the normal number of chromosomes. That's what allows for the production of haploid gametes. And that's what allows for sexual reproduction to exist in the first place. Because when those 2 haploid gametes fuse at the moment of fertilization, they will result in a diploid zygote. Is everybody still with me? All this makes sense so far? Yes.
I guess I just kind of get mixed up with the names when it's like haploid, diploid, like zygote gametes. Is there anywhere you could find like pictures of them? Like a gamete looks like this, a haploid looks like, even though they're 2 different things.
Well, gametes, so unfortunately gametes and zygotes don't necessarily look all that different. Some gametes do. I mean, everybody recognizes this guy. That's a male gamete in humans, flagellated sperm. An egg cell, unfortunately, kind of just looks like a gigantic cell.
And that's a female gamete.
Yeah, it's a female gamete, and then when the sperm cell goes in here, it basically still just looks like this. So the zygote itself,
Could you draw a haploid and a diploid though?
so it'll be coming up later in the lecture anyway,
Okay.
but the big thing there, and I'm just going to use a hypothetical organism that has, let's say, 3 chromosomes. So I'm going to draw the nucleus of this organism right before, I don't know, right before prometaphase. So this would be right after chromosome duplication, right after the nuclear membrane is about to dissolve. And we have our, oh no, this is a terrible representation. Basically, just remember that diploid, die, 2 copies.
2
Is
copies.
that easy to do? Haploid, half. Does that make sense? Yes.
Off of what he's saying, so I was under the impression that a diploid was only a human cell,
No.
and then that haploid was only like fungus.
No.
Okay.
So humans are diploid.
Okay.
It's sort of like a rat is a rodent, but not every rodent is a rat, kind
Yeah.
of thing.
Yeah.
So diploid and human are not interchangeable words. Diploid just means 2 copies of each
So
chromosome.
rather than, and then haploid is just like that one copy.
And haploid is 1 copy.
Okay.
That's all that means. Hopefully that became less confusing and not more confusing. But by the end of this, it should make more sense. So, meiosis, much like mitosis, is preceded by interphase. That interphase is pretty similar to the interphase in mitosis. You have first gap, where the cell grows. You have synthesis, where the chromosomes are copied. And then you have second gap, where the cell does some final preparations for division. It also includes subphases, much like the ones you see in mitosis. So we give them the same name. So you have prophase, prometaphase, metaphase, anaphase, telophase. These all exist in meiosis, and they're very similar to what they look like in mitosis. But because in meiosis we have 2 rounds of cell division instead of just 1, we distinguish those as meiosis 1 and meiosis 2. So the subphases also get numbered. You have prophase 1 and metaphase 1, or prophase 2 and metaphase 2. It's important to keep those straight because there are some key differences between them. Particularly when we're talking about anaphase 1 and anaphase 2. So meiosis 1, what does this begin with? Yeah, prophase, or prophase 1. Very similar to the prophase we have in mitosis. A key difference, though, is that at this point, instead of all the duplicated chromosomes existing as pairs of sister chromatids, those pairs of sister chromatids are actually brought together into groups of 4 through a process that we call synapsis. This is going to be somewhat confusing, but it should hopefully make more sense by the end of this. When I say homologous chromosomes, I mean chromosomes of the same number containing the same genes. So in all of your cells right now, you have a chromosome number 1. You have 2 copies of it, one from mom and one from dad. In your sexual organs, when you're producing gametes, those chromosomes will duplicate, and you'll have a pair of dad's chromosome 1 and a pair of mom's chromosome 1. Those are homologous chromosomes, or homologs, because they contain the same genes. So during prophase 1 of meiosis 1, that pair of mom's chromosome 1s and that pair of dad's chromosome 1s will come together and form a tetrad, or a set of 4 homologous chromosomes. Does that make sense? The reason this is done, and this is really cool, is that allows for the actual physical exchange of chromosome segments between non-sister homologous chromatids. Meaning that one of your dad's chromosome 1s might break a tail off and swap it with one of mom's chromosome 1s. Looks like this. They will actually physically break off pieces of themselves and trade them with each other. This is really cool because this creates new chromosomes that have never existed before. So this is the first major source of genetic variation that you see in sexual reproduction. You're creating all new chromosomes that have never existed in the history of humanity. Now, why does this happen between non-sister homologous chromatids rather than sister chromatids? The answer is fairly obvious when you think about it. It's because the sister chromatids are exact copies of each other. So if you swap the tails of these two, it doesn't make any difference. It's still going to be the same chromosome. But if you swap a tail of this guy and this guy, then you have 2 brand new chromosomes that never existed before. This happens during meiosis 1. Any questions on this process? Now's a great time to ask if you're not clear on all this, because this is fairly important and will absolutely be on the test.
Is this just prophase, or is this all the meiosis one?
You
Them
mean,
crossing over. Like them crossing over
oh, it only happens in the beginning.
only happens in prophase?
Yeah.
Okay.
And then after that, the, happens in prophase 1.
Okay.
Next, we have pro-metaphase 1. Were there any other questions? Okay. You'll notice the theme here, this is fairly similar to pro-metaphase in mitosis. The key difference here is something called independent assortment. This is another source of genetic variation in sexual reproduction. And what it means is that for any tetrad of homologous chromosomes, meaning those